Igneous Rocks, Part 3-2, Magma Differentiation. This lecture follows the Bowen's reaction series. One magma chamber could end up with different kinds of rocks in it. It started with the same magma, but since the olivine, which has the most iron and magnesium, is heavier than the silica-rich minerals, it forms first and falls to the bottom of the magma chamber. Then, after a while, the pyroxene and plagioclase feldspar start forming and start filling up the magma chamber. Finally, the things later in the Bowen's reaction series, until the end of the Bowen's reaction series will be on the top. So as a result, you start off with a very mafic rock on the bottom, and in this case, a rather intermediate rock at the top of the same magma chamber. This happened in the Palisades Sill in New York. The Palisades Sill is a long layer of igneous rock that is along the side of the Hudson River. Now, if you go to it, it's weird because it was injected between a layer of sandstone. So there's sandstone at the top and the bottom. And then there's a layer of basalt next to the sandstone. And then you have olivine, calcium-rich plagioclase, and sodium-rich plagioclase at this, just above it. So that happened in this way. You had a basaltic magma coming up and injecting itself within the layers of sandstone. Now, the first rock that formed was around the edges of that, and that was the basalt. And it was basaltic, it was mafic magma, so that's not a surprise. But inside that magma chamber, all of these olivine crystals were busy forming and falling to the bottom. And when they had fallen, they didn't get a chance to work with the rest of the Bowen's reaction series. So the pyroxene formed, and then the others formed, until finally, the bottom you had a layer of olivine, and at the top you had the plagioclase feldspar. So this is all simply the Bowen's reaction series, going as it is falling into the magma chamber. Bowen's reaction series is going to help us solve some really puzzling problems. For example, if the mantle is made of peridotite, how can it form basalt at the mid-ocean ridge? That basalt is mafic, the peridotite is ultramafic. At the same time, a subducting ocean plate is basaltic. But the magma that forms from the melting comes to the surface to make the Andes volcanoes. It's andesite. Or it could produce granite, felsic. That doesn't make a lot of sense unless you recognize it's the Bowen's reaction series. Finally, why are there continents? The first Earth didn't have any continents. And if there weren't any continents, you wouldn't be here. I wouldn't be here. None of us would be swimming. There would be nothing. So your very existence is reliant upon the Bowen's reaction series, but not forward, but backwards. Oh yes. You need to know the Bowen's reaction series forwards and backwards. Well, here goes. The basalt made from a mantle-derived magma, since the mantle is peridotite. We've got the peridotites down here, and we've got it melting, and it's coming up, and it's making these funny little bubbly things. That's called pillow basalt. So there's basalt being formed at the surface of the ocean crust, and there's gabbros below it. Those are mafic, whereas the peridotite that came up to make it is ultramafic. In fact, if you look at 100 kilograms of the peridotite, which is olivine and pyroxene, it's only 43% silica. But this magma produces 38 kilograms of basaltic magma. Where did the rest of the stuff go? It never melted, and it remained in the mantle. Why didn't it melt? Because the olivine and pyroxene at the beginning of the Bowen's reaction series has the highest melting point, whereas the things at the bottom of the Bowen's reaction series has the lowest. So it's not that all of them melted, only part of it melted. And what did it create? It created a more mafic magma rather than the ultramafic. All of those crystals of olivine and pyroxene could stay behind. So continents are made out of the melting of a basaltic ocean plate. But the fact is, the whole plate didn't melt. It only partially melted. So the more felsic part melted because it has the lower melting point. As a result, the partial melting of the magma made andesite, like the Andes volcanoes, or it could have even made granitic magma, felsic magma. So if you have 100 kilograms of basalt, you'd end up making 14 kilograms of granitic magma, which is 60% silica, and 84 kilograms of pyroxene crystals, which don't melt. They keep going down, becoming part of the mantle. So the mantle keeps getting more and more ultramafic, whereas the stuff that comes to the surface is more and more felsic. Hence, we had our first continents were actually andesitic volcanoes. They were islands, and they just kept growing until finally they became continents. Well, if partial melting of rock gives you andesitic or granitic magma, where would you find mafic lava? Well, you'd find it at the mid-ocean ridge, because that's peridotite, which is ultramafic, turning into mafic basalt, but even more mafic, even ultramafic. Where would you find the most of it? It would be in Hawaii, because it's over that hot spot, and a lot of that peridotite is actually melting. The result is you have green sand beaches, and those green sand beaches are made of olivine. So the most mafic material on the surface is the result of a hot spot. You never find quartz sand formed in Hawaii because the magma that created Hawaii was much too mafic. When a hot spot showed up underneath North America, it first started to melt the mantle. The result were huge basaltic lava flows that created the Columbia Plateau. But the plate, the North American plate, kept moving over that hot spot, and now that hot spot is underneath the Yellowstone caldera. Yellowstone is a megavolcano simply because that hot spot eventually started to melt the felsic crust of the earth, and that felsic magma came to the surface and made a megavolcano.